This video was produced by...
So good evening, everyone. Welcome to our last public science talk for this semester. My name is Chanel Morani. I'm the director of the John C. Wells Planetarium here on campus and a faculty member of the Department of Physics and Astronomy. It's great to see such a large crowd. Thank you all for coming out tonight. Just a couple of quick announcements before I introduce our speaker and we get going tonight. One is that our last public star party is scheduled for tomorrow night, and it looks like the weather is going to cooperate with us. That's often rare here in the Valley, as you all know. It's 1 hour after sunset. Sunset tomorrow is about 5 p.m. That means we'll be on the sky by 6 p.m. That's at JMU's campus east of 81, so behind the Department of Physics and Chemistry, just down the hill from the quad, down the hill from Festival. I encourage you all to come out. Mars will be up. We might hit Saturn. It might be hit or miss with Saturn, but definitely Mars, the binary stars, and we'll show you the 10 stars you can see from Harrisonburg. December 5 to December 21. So December 5 is the Friday night and Saturday night at 7 p.m., Sundays at 2 p.m. One of our most popular shows every year is Mystery of the Christmas Star. It's scientific exploration of what the Star of Bethlehem may have been. We use our star ball, we go back to the Middle East, we go back 2,000 years, we count the precession, and we investigate what the Star of Bethlehem may have been. It's somewhat similar to what Dr. Solontoi will talk about later this evening, about how the ancients, our ancestors, looked at the night sky and tried to decipher meaning. I encourage you to come out. Every show we do at Planetarium, of course, is absolutely free. It's usually our best show of the year. December 31st, I know you guys are thinking about exams, but I'm thinking about New Year's Eve. We're going to have special family shows for first night in Harrisonburg. We'll have shows starting at 6, and we'll do shows every half hour until about 8, as festivities downtown begin for first night in Harrisonburg. And then I just want to highlight our first public science talk in the new semester, in the new year. That's going to be February 12th. We'll be here in Wilson Hall again. In fact, our speaker that night is going to be Dr. Caroline Luber, one of our own JMU faculty. She's a mathematician, but actually does sound experiments from rocket launches down at Wallops Island. In fact, her experiment got obliterated in the last explosion. So I'm sure she'll mention that and show you some really cool photos of what an explosion looks like. Unfortunately, no one's heard, so I can joke about it. So that's February 12, 2015. I encourage you to come out. All the dates, all the information is in our brochure. Our fantastic Planetarium staff hopefully gave you one as you came in. If not, by all means, please pick one up or come out Saturday and you can one at the Planetarium. Okay. So I'm extremely honored and delighted to introduce our speaker today. Dr. Michael Solontoi is our speaker from Lynchburg College. He is an expert in looking at the relics of the solar system, the asteroids and comets. He's involved, has used data from the Sloan Digital Sky Survey, and is involved with the planning for the LSST, a large follow-up mission that's going to supplement or actually replace SDSS. We hope in the next few years. Prior to joining Lynchburg College in 2012, he did postdoctoral work at the Adler Planetarium, so just a little bit bigger than ours, in Chicago. And before that, he finished his PhD at the University of Washington in 2010. I'm delighted to have the opportunity to introduce Michael and actually give him a copy of an autographed copy of Paul Beauregard's excellent book about light pollution. I encourage you to check it out. Paul Beauregard, of course, is one of our JMU faculty on the end of the night. Thank you.
Thank you. All right. So I feel for you with the star party thing. Apparently I can control the weather. All I have to do is plan to take my introductory astronomy course to our observatory and the clouds come in. So let me get this started. Thank you again for the introduction. There we go, and will this work? Let's see. All right. I tend to talk really loud, particularly when I'm in a room, so if I'm deafening with a microphone, just yell at me. So I am Mike Solontoi. I'm professor of physics and astronomy at Lynchburg College, and today, instead of talking about my normal subject, which is killer death rocks from outer space, I'm going to talk a little bit about the rise and fall of rational cosmology in the ancient world. We live right now in kind of the second period of rational cosmology. We're going to take a look at the first one. And what that means, I hope to show you along the way. Mainly, I just want you to be thinking today. Today's more of a thinking and an introspective. One important point, there is a little bit of a difference here. This is Katie Mack. She is a highly reputable cosmologist. She is having her hair done by an excellent cosmetologist. So there's a difference there. Just always have to emphasize that. So let's start with us. This is us. This is all of us. I mean, we right here are in a small room, in a city, in a country, on the planet. And this is us. But step back a moment. I mean, that's really kind of tiny in the grand scheme of things. Voyager 1, as it was leaving the solar system in 1991, spun around and took one last sequence of pictures of the solar system. That's us also, that little tiny pixel, this guy. Right there. That's us. All of us. If you were alive in 1991, Valentine's Day, very appropriate, Valentine's Day, 50% chance that you're in that picture. I was outside waving, you can tell, right? Shockingly, actually, we should only be filling about 1/16 of a pixel there. That's us. We are tiny. And the universe is vast. This is part of the Hubble Ultra Deep Field. There are 3 stars in this picture. Everything else is a galaxy. Every speck of light. This right here, 200 billion stars, 500 billion planets. 500 billion planets, 500 billion planets. That's a star, 500 billion planets. Frighteningly large, and we're trying to make sense of it. And that's what makes us wonderful. That's what makes us, we're curious about this. We want to figure this out. I have to relate this to my own field. We landed on a comet just a couple days ago. Why? Because we want to figure out how it works. We're frustrated. We don't know where these things come from. We look at the Earth, we go, the Earth shouldn't have water. Where did the water come from? So we go to comets, we go to asteroids, we explore, we try to figure things out. We look at a rock. That rock's there. I don't know what's under it. What am I going to do? I'm going to kick it over. I'm going to look at it. I want to go way back, though. Before spaceships, before telescopes, before very bright lights in my face, to where you had the night sky. This is what we have had for thousands and thousands of years of human history, and thousands of years of unrecorded human prehistory. This is the night sky. Without a telescope, you're limited to what you can see with your eye. And ancient civilizations had a lot of time, so they spent a lot of time looking at the sky. So what do you see in the sky? You see stars, you see the sun, you see the moon, you see planets, you see other things. And after you sit there and look and think and record for years and years and years, you recognize that there's patterns. The sun, the moon, the stars, they circle the sky night after night after night after night. And you write this down, and it's a big part of your life. I mean, you can argue that astronomy may have been the very first science. It's either astronomy or medicine. It's whether Oog the caveman walked outside like, ooh, what sky? Or, ooh, why do red berries make Oog sick? It's either astronomy or medicine, one of the two. I tell bad jokes, get used to it, it's okay. But every culture noticed this. You can't not notice it. I guess if you're living underground, but the Egyptians, their cosmology, the vault of the stars, the earth below, the gods riding around above. Hindu cosmology, the earth below, the starry vault of the sky. This is kind of cool, it's a big speckled hooded cobra, that's the Milky Way. Mayan cosmology, the earth below, the sky above, the stars, the gods riding above it. The sun, the moon, the stars, the sky circles the earth. The Egyptians, the Middle Kingdom, not the Egyptians, the Chinese, the Middle Kingdom, in the center. The celestial heavens, the planets, the gods riding around. Everybody, even made up stories, have it. It's common. And if you think about it, it makes sense. Take away the telescope. There is nothing that's telling you right now that we are moving through space at some absurd speed, right? The Earth is spinning, and we're going around the sun's going around the Milky Way is falling into Virgo, Virgo's falling into Coma, blah, 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 and we're expanding and accelerating. I don't feel like I'm moving at some ridiculous speed. Until you get a telescope, you really don't have any empirical visual cue that we're not just sitting here watching everything roll by us. So we come up with these cosmologies. The other thing we do is we give names to things. Every culture out there gave names to the stars. So here's, over here, I'm not sure if you can necessarily say, this is what we would consider Orion. You can see the 3 stars up there. That'd be the Egyptian constellation Sa. If you were Chinese, it would be the 3 stars and the Jade Well. Here's some little cartoons showing kind of a modern view of Orion. And over by him is the bunny rabbit and the big dog and some other things. Completely beside the point, I have to point this out. This is my favorite constellation. This is the constellation of Canis Minor, the little dog. It's 2 stars. So, man, the sky is full of dogs. I mean, it's just, they're just dogs. Anyways. You name things, you make a story, but then you sit there and because you don't have anything else, there's no television, so what are you gonna do? You're gonna watch the sky. You notice that things don't necessarily fit into this cosmological picture. There's some issues. The path of the sun. If you're really paying attention to it, the sun doesn't traverse the same amount of sky all the time. It falls through the constellations of our zodiac, although Ophiuchus somehow got left out, poor Ophiuchus. But the sun kind of speeds up and slows down. And that's a little troubling. I mean, we don't really understand why that's happening here at this point. I mean, we do, but they don't. Another troubling thing. The moon changes size. This is a simulation of the moon through an entire month. The phases are shown here, but you notice it sort of does this sort of belly dance thing. It gets big. You can see a little bit more of one of the sides. The ancients noticed this. This was a big, big problem. Why does the moon grow and shrink a little bit? And if that gave them problems, this really did. This is a number of pictures, exposures here of Mars. That's what the red ball is here, moving on day by day by day by day. And if you're watching Mars, every time Mars goes into the southern sky, it does something funny. It goes along, it goes along, it goes along, and then it stops, and then it starts going backwards. Well, that's not right. And then it stops again, and then it starts moving forwards again. Every time it's due south. And it's not just Mars. Jupiter and Saturn do the same thing. And then Mercury and Venus do this weird thing where they just kind of slosh back and forth across the sun. Weird things. It'd be nice to explain those. And there's just truly bizarre things. These things show up in the sky. This is a comet. I love comets. That's Hale-Bopp. The Babylonians wouldn't have seen that one. But that's Hale-Bopp. They come out of nowhere. You can't, no matter how good your records are as an ancient people, you can't predict these things. Sometimes the moon takes away some of the sun. Sometimes the moon takes away all of the sun. So it's a confusing place, and a big part of our cosmological heritage is doing exactly what the ancient Mesopotamians depicted here in this bas-relief carving. This is the god Marduk chasing away the chaos monster. Woo, sorry. I'll avoid talking over there. We're chasing away the chaos. We are making sense of the world. What are at this point, we're talking about the Sumerians. We're talking about peoples who lived 4,000 years ago. What were they doing? They were trying to make sense of a very confusing world that made them feel very small. Remember the pale blue dot? Remember the Hubble Ultra Deep Field? We are engaged in the exact same activity today. 40 centuries ago, the Sumerians wrote down and tried to account for the motions of Venus on one of the oldest astronomical tablets that we ever have. Flash forward 40 centuries later, we are currently trying to unravel the mysteries of the Big Bang itself based on patterns left in the sky by the Big Bang. Different patterns, same exercise. For all of human history, we have been asking the same question. Where does it all come from? What does it mean? What's going on? But we haven't always asked that question the same way. More importantly, we haven't always accepted the same answers. The answers we accept are based culturally. The answers that we accept are a completely different answer than what the Sumerians would have. So let's go back. Let's take a look at what the Sumerians would have had to say, or the Assyrians or the Babylonians. I don't speak ancient Urdu, so couldn't really ask them. But let's take a look at our cosmological roots. The Mesopotamians left some of the very earliest of all astronomical records. And the Mesopotamians had an idea, and it's kind of a logical one. The sky, you can't touch it, right? What else can't you touch? The gods. The supernatural, the stuff that isn't normal stuff, is the sky. And what we are, and the dogs and the cats and the cows, are the natural, the earthly stuff, the people on the ground. And there's a clear separation between these two things. It's also important to point out that to the Sumerians, they weren't ever building a model. They were making many predictions. But to them, the sky was just a large two-dimensional mosaic showing what the gods were doing. And that was important because if they could stare out and look and study and find patterns in it, they could let the supernatural guide them. They could see what they should be doing based on what the gods wanted them to be doing. You can find this throughout their writings. When Marduk's star is doing this, it's time to plant the corn. Marduk's star is one of the planets. Ishtar's star is Venus. When Ishtar's star is doing this, you should harvest the crops. They identified and codified these patterns. They did it exceptionally well. They worked out the cycles of the sun, the cycles of the moon, the cycles of the stars, the cycles of the planets. In fact, their records were so good that it wasn't until midway through the Enlightenment that we actually had records that outdid them. They left such a volume. Now, their exact angular measurements, not perfect, but just in volume. They left thousands of years of these records. The planets were important to them. Why? They literally were their gods. The gods literally were these planets wandering around through the skies. In this sense, the astronomers were the priests. What were the Mesopotamians after? Their cosmology was a cosmology of necessity. It was a cosmology of phenomenology. They were prophets, because the sky was prophecy. It wasn't something to be understood. It was something to be charted. And that's a perfectly good answer for them. They were astronomer priests. And most cultures accepted this type of cosmology, where it was the priests, the really smart religious folks who went out and could chart the stars and figure out what's going on. And in some sense, it's true. If you understand the precession of the star, the motion of the stars and the sun and the moon, you can run agriculture really well. Calendars are incredibly complicated. You might think it's easy to tell time. Time is really tough. Seriously, I'm not just, look up some point how you tell time. It's amazingly complicated. But this idea of kind of prophecy gets turned on its head by the time we get to the 6th century of BCE. At least in one part of the country, the Ionian coast, sort of the Mediterranean side of Turkey. At this point, we have a group of people who, for lack of a better term, were kind of bums. They just kind of sat around and thought. They just sat and thought, and they thought the deep thoughts, and they argued with each other. And for the first time, really, in history, they weren't so much wondering, just charting things down, just writing things down, just figuring out patterns, but they wanted to know how things moved. They wanted to know why things moved. They tried to come up with explanations for why these things were doing what they did. And this is a radical departure from what the pre-Ionian cultures were doing. They had focused on signs and interpretations. Why did you study the sky? So you know what the gods are telling you to do. These early Greeks, these Ionians, were much more interested in a thought process that we're a little bit more familiar with, cause and effect. Why did we go to the comet? We want to figure out how the comet works. We want to learn about the comet's surface. Turns out it's really hard. This is Raphael's School of Athens. This is my favorite piece of art in all of history. It's sort of just like a Where's Waldo of everybody in classical antiquity thought and art and so forth. And then Dante snuck in there for reasons. But otherwise, it's all Greeks and Romans and Egyptians. The Ionian cosmology, if you want to call it a cosmology, is more of a school of thought. Your first big Ionian thinker is Thales, and he has a whole crew of people who follow him. But the whole idea is that they had some rather radical thoughts. Number one, They said, it's like, you know what, the heavenly bodies are interesting. These planets are doing their own thing, but you know what, that's not really Zeus up there doing that. It's not really, those aren't really the gods. It's something up there. They also thought that the whole universe was made up of stuff. There was some basic substance. Some of them argued that it had to be fire, had to be water. We get kind of our 4 classical elements out of this. The stars might not really be things. I mean, they're just kind of points of light. I mean, even with a telescope, it's hard to show that they're not just a point of light. Thales himself said that perhaps the stars were, the sky was just an immense, giant bronze shield, right, that had holes poked in it. And there's some giant light outside shining through these holes. They also had this miraculous idea. It's like, you know what? I bet the moon's just reflecting light from something. That's kind of shocking, a non-self-luminous moon. They did recognize that whatever was up in the sky really behaved a lot differently than the stuff down here. Stuff in the sky just kind of goes around in circles, right? If I have a rock here and I let go, what happens to the rock? I teach for a living, occasionally I ask questions. What happens to the rock? It falls. But the stars don't fall, the planets don't fall. So there's clearly something different between heaven and earth here. And so they came up with theoretical models, this bronze shield. I mean, they weren't necessarily kind of scientific models that we would say today. I mean, you can't really go out and test them. But I mean, come on, we're what? 1,000+ years before Bacon writes down what we find in the appendix for the scientific method. With the Greeks, though, we see that they place a big role on these models. Their geometry, their mathematical axioms was the foundation for the world's order. To them, numbers, if they could fit a number to something, that was actually a natural phenomenon. If it took an exact amount of time for the moon to go around the Earth time and time and time again, that meant something. And they came up with fantastic models. Pythagoras came up with a beautiful, big wall of text, I'm sorry. Pythagoras came up with a great idea, this beautiful thing about harmonious motions. And he said, he would have said this in Greek or something, not English, but the bodies in the planetary system revolve around the center at distances related by mathematical proportions. Some revolve more quickly, others more slowly. The slower ones emit deeper sounds as they move, and the quicker ones higher sounds. These sounds depend on the ratios of distances, which are so proportioned that the combined effect is harmonious. Oh, that's pretty. That's very pretty. This actually gets picked up again and again and again. I mean, Kepler devotes a huge amount of writing in the 1600s to the harmony of the spheres. Pythagoras was kind of an odd duck, honestly, a little bit of a mystic. He was a mathematician mystic, which is kind of cool. If you've ever taken algebra, you're familiar with the Pythagorean theorem. Pythagoras also showed that the square root of 2 is what we call an irrational number. That means you can't divide one number by another and get the square root of 2. And this excited him so much they went out and sacrificed 100 ox to Zeus over a number. This brings up a very, very important point. This is Fred Flintstone and Barney Rubble. They portray cave people. Are they real cave people? No. The Greeks were weird. The Greeks are not us. Do not pretend that our culture, our understanding, our way of thinking was their way of thinking. You can't help but do it. But keep in mind that these people lived a very long time ago in a very different world. I mean, when I learned that the square root of 2 is an irrational number, I thought it was pretty cool myself, but I'm not going out and slaughtering livestock over it. So just always keep that in the back of your mind. The Ionian, we didn't stop at the Ionians. It started a real realm of thinkers thinking the deepest thinks. This is from the School of Athens. That is Plato on your left and Aristotle on your right. Plato thought so hard he tapped his head a lot, which is why he's bald, right? No. But this is the 5th and 4th century BC. This is the golden age of Athens. This is the golden age of Greek philosophy. Plato turned his attention to everything. I mean, these guys thought about all the thoughts. And when Plato turned his eye to cosmology and astronomy, he looked at what the Ionians had been doing. He looked at the sky, and he came up with 2 ideas, fairly sound ideas. He said, 1, everything in the sky should consist of uniform circular motions. Why? The circle is a pretty gosh darn spiffing figure. The circle is kind of a perfect figure. It's really nice. And if the heavens really are kind of perfect and special, they should be circular. And again, I don't feel any wind. There's no reason to think that we are the ones who are moving, so that all of these uniform circles that are carrying the sun, the moon, the stars, Jupiter, Saturn, Mars, Venus, Mercury, are all concentric with the Earth at the center. Now, they're all rotating at different rates, but they're all on a common axis. And to this, Plato signed his name in big letters, Plato, and walked off into the sunset. Because Plato really didn't do all that much math with it. And if you notice that his model, just these 8 spheres, why do you need 8 spheres? You got the stars, the sun, the moon, Mercury, Venus, Mars, Jupiter, and Saturn. It doesn't explain things. For example, there's Mars doing its little retrograde backwards motion. If all Mars is doing is going around in a nice uniform circle, how do you get that? You don't. Plato's idea didn't work out all that well initially, but thankfully he had a pair of minions who fixed up the model a little bit. Eudoxus took it and go, gosh, Plato's brilliant. I bet I can make this work. And he found by adding circles between them, he could kind of change things around a little bit. And he added enough circles to make 27 circles to make the 8 motions of the skies. And it got really, really good. And then his buddy Callippus comes along and goes, actually, I can do you one better. If I use 34 spheres, we can get even better accuracy. And now we're cooking. We've stuck with Plato's axioms, these great ideas, uniform circular motion, concentric with the Earth, and we just have to add a bunch of extra spheres. We are slowly but surely mechanizing the universe. We're actually creating a model for why these things move around. Enter Aristotle. The history of Greek philosophy of Socrates, who taught Plato, who taught Aristotle, who taught Alexander the Great, who dropped out of school and conquered the known world. I'm not sure if that's really a good lesson or not. Anyways, Aristotle took this up. Aristotle wrote voluminous texts on everything. And he asked a really gosh darn good question after Eudoxus and Callippus comes along. It's like, are these spheres that we've been talking about, are they imaginary? Are we just kind of noodling around? Or are these spheres real but somehow invisible, just untouchable by us? Oh, and by the way, I fixed your model. If I use 56 spheres, I can nail things perfectly. And it was a really pretty gosh darn good. It didn't explain the moon getting bigger and smaller, but it did a lot of really nice things there. He had fully mechanized the universe, and he asks a really good question. He says that if we have a model that perfectly replicates the universe, doesn't that imply that that model might actually be true? That's a radical departure from, I have a book where I have recorded the position of Venus for the last 1,000 years. Using algebra, I can now figure out where Venus will be tomorrow. Just prediction, just predictive manner. This is actually, well, if Venus is on these spheres and we get the outer one spinning, this whole thing just hangs together. Ooh, more deadly wall of text. Aristotle, here's a nice bust of Aristotle there as well, emphasizes something that we've been getting since Plato with the ancient Greeks. The heavens work in terms of understand. This is amazing. We can understand things. Why did we go to the comet? Because we think us, little fleshy bags of carbon and water, can understand the entire universe, where the solar system came from, where the solar system's going. Same sort of idea. The heavens work in understandable, permanent principles, stuff that doesn't change. These principles can be visualized by a theoretical model. And we recognize, however, that our model might not be exactly what's going on. But it's okay because we can take a step back and look at the model, and we can compare how good our model is to what's going on. Or in his words, you can mentally stand outside the cosmos and contemplate its structure and mechanism. These are human beings saying, we can understand everything. That's big. That's neat. This model as an abstraction also gets Aristotle out of a sticky wicket. He doesn't perfectly model retrograde in his cosmos, nor does he get the variable size of the moon. This whole idea that the heavens are perfect and we on the earth are not kind of gives him a little bit of weasel room. And then he sort of sets this aside and goes writing about ethics for the next several years. I'm going to take one more jump in time. So that we talked about the lands of Sumer. We talked about the Ionian and the classical Greek thinkers. Let's jump forward one more time to the 1st and 2nd century AD. This is the Roman Empire now at its height, spanning the Mediterranean. Very importantly, the Roman Empire brings direct contact from the Greek philosophers with their high and mighty thinking and ideas with the Babylonian prophets, the Babylonian priests, and their impeccable record keeping and their amazing algebra. And right in this confluence, we have a rather unique individual. Ptolemy, 2nd century AD. He lived in Egypt, wrote in Greek, and was a Roman citizen. And he decided that he was going to fix this whole cosmology thing. So he starts basically with Plato's idea. What I'm going to do is I'm speaking as Ptolemy, this isn't me. I'm going to take the Earth, and I'm going to let's say that's Mars, right? It's red, so it should be Mars. Good choice? Cool. All right, I'm going to take Mars, and I'm going to put Mars on one of these circles, or I'm going to just call it a deferent. I'm going to name all these things to make people have difficulty with the vocabulary in later years. But I'm going to call it a deferent, and I'm going to put this on the deferent, and I'm going to spin it. And this is Plato's model. Now, what doesn't this do? This doesn't do retrograde. We need to figure out a way of making Mars go backwards. Well, Ptolemy had this great idea. Who says the circles necessarily have to be concentric? What if I put a circle on a circle? Hey, I'm going to call this smaller circle an epicycle, again, because I hate vocab students. And I'm going to let the Mars spin on the epicycle, and then the epicycle is going to be carried around the Earth on the deferent. So now you can sort of see what's going to happen. It will do little loop-de-loops. It will retrograde in the sky. Oh, but this still isn't working quite right, because if you really study, now that we have the Babylonian records, Mars doesn't move at a constant speed through its entire orbit, through its entire path in the sky. I almost said the word orbit, which we shouldn't use at this point. So why don't I just move the Earth off the center? Now we have a different viewpoint at Mars, and that helps explain a little bit of the brightening and darkening of it. And this still isn't working. Well, what else can I do? Let me make another highfalutin word. Let's call an equant. I'm going to create an equant. This is another point in space. And what's special about the equant is that it's the equant that the deferent actually executes uniform motion with respect to. This is getting awfully complicated, isn't it? But it works. It works beautifully. It works so well that you always say the Copernican revolution, right? Copernicus's mathematics, by putting the sun at the center, did no better job than this. The next improvement in terms of predicting where planets were going to be isn't until Kepler says the heck with circles and moves us into a completely different geometry. How this works, if you're having difficulty visualizing this, the fine folks at the University of Nebraska-Lincoln have a beautiful little, slow, hello, come on. There we go. Have a beautiful little model here. I'm not sure how well it can be seen from even the better seats, let alone the cheap seats. You have the Earth, the center, the deferent. Here's the equant. There's the epicycle. Mars is the red dot, and you'll watch the little loop-de-loop that Mars executes. Let me start the animation here. There it goes, and hey, little loop-de-loop. Everybody see the loop-de-loop? More or less? Otherwise, you can just do your favorite search engine search for it. And it has all the different planets in here. You've got Mars. We can see what Jupiter does. Oh, Jupiter moves slower. Not surprising. You can make up your own planet, something like this. It's kind of fun. You can play around with it. But this works fantastically as far as if you want to know where a planet is in the sky at any given time. It works beautifully. And, it even remembered where I was in my talk. But here's something else. Ptolemy fixes this up. But what Ptolemy notices, just like in this simulation, I had to change all the numbers for Jupiter. All of these epicycles, all of these difference, all of these equants, all these difference were unique per planet. Ptolemy had to solve each planet independently. Mars had its own solution. Jupiter had its own solution. Saturn had its own solution. Venus and Mercury had their own solution. There was no connection between them. If you think, wait, we just lost something, right? What was so neat about Aristotle's model? You set the sphere of stars spinning, and the whole thing goes. Everything just works like clockwork. Here, there's no connection between them. Every single planet in Ptolemy's model is independent. There's no longer any unifying theme. What we've done here with Ptolemy is taken a giant step backwards. We have now ended rational cosmology. We are no longer thinking like Aristotle, like Plato, like Thales. We are no longer looking for the hows or whys. We are simply looking for sign and interpretation. We are simply looking for a method to predict where the planets are. Ptolemy, in a sense, abandons physical cosmology in order to save the phenomena. The phenomena here are the planets and moons moving across the sky. He says so himself in his Almagest. The Ptolemy's main work is the Almagest that everybody knows. Actually, if you ask Ptolemy, he wouldn't say it was the Almagest. We'll get to that in a moment. But the Almagest is this big compendium of Ptolemy's mathematical works, his astronomical works. The systematic study of mathematical theory alone can yield its practitioners solid conclusions free of doubt. Oh, this is good. This, then, was the sort of theory we decided we should study. Oh, excellent. Concentrating on its application to things of a divine and a celestial kind. Ptolemy isn't interested in why the heavens work. Ptolemy is not interested in explaining our place in a very confusing, chaotic universe. Ptolemy is looking for fate and occult knowledge. If you ask Ptolemy what his main work was, he wouldn't tell you the Almagest. He would tell you that his main work, the one that he's going to be known for, is the Tetrabiblos. The Tetrabiblos is basically his astrology book, telling you how to live your life in accordance to the stars and planets and sun and moon. And the Almagest is simply the instruction manual for the Tetrabiblos. For those of you who are mathematically inclined, you pick up the Almagest and you can make the Tetrabiblos work. Saving the phenomena. We're no longer dealing with rational thinking to its conclusion. I'm not knocking Ptolemy at all, by and large, not an iota. The mathematics that he puts up here is brilliant. In fact, it's so good that Ptolemy's epicycles and Ptolemy's cosmology survive until the Copernican Revolution. This is Peter Apian's Cosmographia, published in the 1500s AD. This is Ptolemy's cosmology, not changed a jot in a millennia and a half. And as I said, one of the knocks on Copernicus's early works is that it didn't predict the sky any better than Ptolemy. Replace the sun with the earth. You're still doing it. In fact, Copernicus, the only thing Copernicus is you can, if you use a little bit more advanced mathematics, you can get the answer a little bit quicker. Only advantage it has. In fact, actually, I really do want to point out something very important about Ptolemy. Ptolemy was actually onto something. Those of you who've taken a bit of physics might be familiar with this gentleman here. This is Fourier. Fourier came up with a method of analysis and an absolutely brilliant idea. It completely, it's in everything we talk about. This microphone I'm talking into right now does Fourier stuff. Fourier pointed out that any sort of signal, any sort of pattern, he could replicate any sort of periodic pattern, any sort of signal, like maybe sound, by stacking up an appropriate number of different waves. So here we have a very complicated looking wiggle, 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 but according to Fourier, if he added up all of those little regular, very easy to calculate wiggles, he would get the complicated one. Ptolemy, despite being, okay, what are the dates on his life? 1800. Okay, Ptolemy, despite being around 1700 years prior to Fourier, basically has hit upon the same thing. I have a little animation here that I want to play for you. You can, using Ptolemy's epicycles, in fact, if you don't stop with just one epicycle, you can match planetary motion perfectly. If you add an epicycle onto an epicycle onto an epicycle onto an epicycle, you can match any motion. So here is the reconstruction of a planet's orbit using an absurd number of epicycles and deferents. So here we go. I'll start playing here. Right, and there's a, I think, there we go. So while this plays, I'll comment on this for a little bit. I do want to point out something. I'm a professional astronomer. I do a lot of dynamics work. Guess what I do some of my calculations in? Epicycles. Why? It's easy. The planetarium here, that beautiful the mechanical planetarium, the projector version of the planetarium. What's that? It's basically epicycles. That is a Ptolemaic universe there projecting the sky. So check this thing out. Okay, the little dotted line there is where the planet is. Look at this thing. This is just a truly bizarre planet, right? I don't know how many circles are there, but you can literally replicate anything. Given the proper number and size and speed of these circles, you can replicate any pattern. I do planetary dynamics. I do galactic dynamics. There's a textbook they give you in graduate school in astronomy by Binney and Tremaine called Galactic Dynamics. It's for how to calculate the positions and paths. Okay, I know we put the pen down here and we're actually showing you what the path in the sky looks like. This book on galactic dynamics models the orbit of the sun and the galaxy on epicycles. Why? The sun is, oh, this is looking really weird. The sun has a rather bizarre path through the galaxy. And is it real? This is really strange. That's a heck of a planet's orbit, isn't it? I've never watched this all the way through. I hope it's not anything weird. Huh. You can replicate anything with epicycles. So, yeah, I'm not kidding about the Galactic Dynamics book, actually. Really, if you want to plot how stars orbit in a galactic potential, you typically use epicycles, because otherwise it gets very, very complicated, very, very complex, very, very fast. And for that, I welcome you into the second age of rational cosmology. Notice the way we're thinking of things these days. Again, we don't want to put our thoughts and feelings into Aristotle and Plato and Thales, but we're asking those same questions again. We're asking those exact same questions. And to me, that's what makes science worth doing. That's why I do astronomy, because I want to know things. Not only that, and here's the big difference between us and the Greeks, I think. I like being wrong. If I'm not wrong about things like 3 times a day, I'm having a boring day. Why do I like being wrong? You learn from it. It means you learn things. If you just spout out things out of your mouth and everybody just nods with you, you're not learning. The idea is you put an idea out there. And if it's right, it's great. And if it's wrong, you've learned from it. And it's fantastic. And to me, that's what my job is. I have the best job in the world because I am someone who is professionally wrong about stuff. And I get rooms full of people to listen to me talk about my ideas. So for that, I thank you. And again, I thank you all for engaging in a bit of rational cosmology. I'd like to thank these fine fellows at other institutions who I've spoken with over the years, and a lot of them, in particular, Paul Boynton at the University of Washington really put the whole germ of idea of this thesis of the rise and fall of rational cosmology in my head when I was chatting with him back in 2005. So thank you very much. Oh,
yeah.
yeah. On, off,
That'll work.
on. All right, it's off now. Or I'll leave it on. Okay, sorry. I don't know.
So Michael's graciously agreed to have some question and answers. So we have the house lights on. We have 2 microphones up in each of the aisles. And by all means, feel free to ask questions. We'll have a lively discussion. Have the lights on, please.
These lights are on.
Don't want to step up, not be shy.
I also do like real astronomy too, so sometimes.
Go ahead.
Should I speak from my seat?
Absolutely.
I can hear you.
Did you happen to notice you said that one astronomer went from talking about astronomy to ethics? Did you happen to see if any of the astronomers have connected their astronomy with the way you should live your life explicitly?
Well, I do because I am an astronomer, so astronomy lets me live my life. It's tough. It's man. To be perfectly honest, and the philosophers in the audience can throw things at me, I find reading Aristotle a bit like reading real estate leases. I find it very, very dry, and I really have to struggle through it. I mean, Aristotle, I was alluding to one of Aristotle's major works is the Nicomachean Ethics, and he has all sorts of great ideas in it. I don't know. In terms of how you should live your life based on the sky, well, in some ways I think having a bit of a cosmic perspective of things puts you in your place, right? I mean, in the grand scheme of the universe here, I mean, it's just us. This is all we've got. I mean, that was Carl Sagan's bit on the pale blue dot. That when you look at that picture, and I still got this up here. I wish I could talk backwards. That'd be so cool. That'd be the best way to end a talk. We just do the whole thing backwards. There. That little dot. I mean, what Carl Sagan would say about this thing is, I mean, that's us. Think about every single person who has ever lived. Good people, bad people, kings, villains, priests, preachers, scientists, dog catchers, dogs. Every single person who has ever lived, or until we figure out a way of traveling the stars, will ever live, is on that little thing that looks like just a speck of dust suspended in a beam of sunlight. So in that sense, thinking about astronomy really does it grounds you. At the same time, I find it also a very uplifting thing. I mean, here I am, able to say things about not just our planet, but other planets, and our star, and other stars, and other galaxies. I can tell a pretty convincing story back to when the universe was only 10 to the minus 10 seconds old. After that, I have to admit, I'm probably making stuff up. 10 to the minus 10 seconds. That's ridiculous. I can tell a pretty good story of how the universe is going to finish off. I can tell you about when the sun is going to make life on this planet as we know it impossible. I can tell you when comets are going to come by. I can tell you what comets are made out of. I can tell you what planets are made. It's fantastic. And here I am, just this little sack of carbon and water that's somehow able to do this. I think that fact that we strive for that we engage in that activity is really the thing that makes us human. But I'm an astronomer, so I might be biased on that. So.
Is there any record of these ancients ever observing comets?
Yes.
How do they deal with that?
Not well most of the time. A lot of them saw them as portents of doom, right? This giant thing out of the sky. Chinese records of comets go back, depending on how you squint, there's a set of fortune-telling bones from about 1500 BC that may or may not be recording a comet. Not counting that the Chinese had a lot of very good comet records going through the ages. It's actually really interesting. You can trace, you can find records of Halley's Comet going back through a number of things. There was, I think it was a king of Assyria. I don't want to speak out of turn. If anybody knows the history, there was Halley's Comet came by and made a very strong impression on, I think it was an Assyrian king, and he had the comet emblazoned on his crown, and it was on the coins that were pressed for that kingdom. You mentioned that Planetarium is doing a Star of Bethlehem type of thing. Giotto's famous painting of the Adoration of the Magi. Giotto paints a comet as the Star of Bethlehem, mainly because Halley's Comet had just come through the sky, and it inspired Giotto to paint this. So it really depends on the culture, whether they saw comets as good as bad. Even recently, Halley's Comet in 1910 caused huge panics because we were going to pass through the tail of the comet. And guess what gas that we, with our fancy new science equipment, guess what gas we had just discovered in Comet? Cyanide. The comet was going to kill. No, there were like huge articles written by professionals that were in the paper saying, the fears of the comet are groundless. It's not going to do anything. But they're scary because until very recently, we couldn't really predict what they're doing. Even today, long period comets, Hale-Bopp. We did not know Hale-Bopp even existed until about 6 months before it came by. Why? It came in from part of our solar system that's so far away that we cannot see. Hale-Bopp, the comet itself has about the same color as a charcoal briquette. So put a charcoal briquette out past Pluto. How easy is that to see? Not easy. We can't, actually. You could point Hubble at it for days and you'd never see it. So, I mean, even today, comets are still a little bit troubling. For me, they're troubling as a dynamicist because when they get close to the sun, they start firing off their jets and they start skittering around. So a comet tends to orbit the sun like a really well-thrown knuckleball. Like, I could tell you what year Halley's going to come back. Actually, I can't right now because I don't know it off the top of my head. I don't like numbers. But I could calculate and tell you what year and even what month. I wouldn't be able to get better than about a day. I couldn't tell you the exact time when Halley's going to pass by the Earth. For an asteroid, I can tell you down to the minute when it's going to come by us. So comets are a little bit frustrating even today. So some people saw them as beautiful, some people saw them as scary. Same thing with eclipses. Eclipses are big time scary. All of a sudden the sun goes away. I mean, it freaks the animals out. In a total solar eclipse, birds will go roost. I mean, creatures go, oh, it's nighttime. I'm going to go to bed now. It really messes with people. So, excellent question. Yeah.
When you were talking about the ancients, or before Ptolemy and then Ptolemy, I'm not quite sure I understood when the cosmology ceased being rational or why. I mean, so, they're both using math to describe a pattern.
Right.
And one solution was for all of the planets at one time, and then Ptolemy's solution was a unique solution for each of the planets.
Right.
And then that was no longer rational.
I'm kind of using the word rational in a kind of a sciencey sort of way rather than a capital R rational philosophy way. What I'm basically arguing is that there's this period of about 200-300 years from the rise of the Ionian thinkers to the collapse of classical Athenian society around the time of Alexander the Great, where people not only pondered cosmological questions and tried to predict how the planets moved, but actually came to try to come with explanations. To Plato and Aristotle and the others, and Thales, their models of the heavens, they were more interested in explaining how and why these motions actually happened than getting the nuts and bolts right. By the time we get to Ptolemy, what we see is that Ptolemy gets the nuts and bolts absolutely spot on. He can make beautiful predictions, but he's no longer giving a single jot towards why or any sort of unifying theory. What does it mean? Ptolemy isn't thinking about that. Ptolemy is working with this mathematics in order to make predictions of locations so that he can tell your future. He's soothsaying. He's no longer trying to predict the mechanism. In a sense, he's gone all the way back to the Sumerians who said, we can give you a very accurate description of what's going across the sky. but we're not going to tell you what it means. Why? It's unknowable. It's just the gods doing their things, but they always do it in this pattern. Full stop. It's just not in their wheelhouse to look for an answer. And that's why I mean that the cosmological question has been the same. We've been asking the same cosmological question since humankind looked at the sky. What is it, what does it all mean? The specific answer varies from time to time and culture to culture. The answer we expect now, some sort of reason, some sort of overall explanation, was something that is new, only comes up about the time of the scientific revolution into the Enlightenment to the present. Prior to that, it's all mysticism, except for this brief little window in, where a bunch of people on the Ionian coast and in Athens sat around and didn't do much else but think and ask other people to think.
Are you saying that we're in the second rational period now?
Yes. At least I hope we are. I have a job doing this, so my guess is yes. That's one piece of evidence.
You said a major problem was the ability to validate the hypotheses?
Yes. Yes.
Competing views, like you mentioned like Ptolemy and Aristotle, were there like other views in that people just didn't follow? Or?
Yeah, this is, that's the main thing. We don't have, the Library of Alexandria was burned several times. We don't have a complete written record of all the Greek writings. We have a lot of writings of Plato, we have a lot of writings of Aristotle. We don't have complete works. So we don't know all of the different models. I also glossed over a whole bunch. Each Ionian thinker, there was Thales and then Anaxagoras and they all start with A. They all sort of had a different thought. Like one of them put forth an argument that everything had to be based on fire. Another one thought everything had to be based on water. Another one comes along and thinks they're mixture. So yeah, I did gloss over a lot of it. There's a lot of different thoughts. And that, I think you hit on something that makes us a little bit different, right? In the scientific method here, what do you always do? What makes a scientific theory good?
Test it against observations.
You test it against observations or models or you test it. That's what's lacking. That's why that's my Barney Rubble slide there, right? Don't put the scientific method on the Greeks. They weren't experimentalists. Aristotle, Plato never did an experiment. They thought really deep thoughts, they wrote down their thoughts, and then they moved on to their next topic. Sometimes they'd come back and argue about their thoughts. They never did any predictive correction. They never did any modifications of their model in the face of evidence. That's something that sets us apart. And that, again, that's my Barney Rubble slide there. You don't want to necessarily put our, oh gosh, when you read Aristotle and you read these guys, it's like, oh, they're almost doing something. They're not quite there yet, almost. It's really tempting to read the scientific method into what they're doing, but they don't. They don't do that all-important, let's be wrong about something. Let's be happy about being wrong. In fact, actually, I think if Aristotle was proved wrong on something, I think he'd probably punch you in the face. He was kind of a, maybe, I don't know. I always got that he was kind of a hot-tempered guy. He'd sick Alexander the Great on you. There you go.
So you said that as an astronomer that you have predictions about like how the universe might end. And
Yeah.
I was actually curious about like what those might be.
Yeah, okay, so in a nutshell, if today's concordant cosmology is correct, that we live in an expanding universe that is dominated by dark energy, whatever that might be, that's causing the universe to currently accelerate. This means we are headed towards a cold death. The universe will never overcome this. Everything will drift further and further apart. And so if you like looking at stars, enjoy it, because it's only going to last for a couple more 10 to the 15 years or something. It's still ridiculously long periods of time, but basically the era of stars will come to an end 10 to the 15 years from now, which is an absurdly long period of time. What's going to happen is that things are going to be so far apart that eventually the galaxies are going to turn all the available gas and dust into stars. Those stars are going to die off. The dead star dust is going to turn into stars. They're going to die off. And you're going to have a universe made of nothing but degenerate objects, things like white dwarfs, neutron stars, and black holes. You wait long enough, the neutron stars, black holes, white dwarfs will all collide, accumulate, so now you have a universe made up of nothing but black holes and particles and energy. If you believe Stephen Hawking, these black holes will slowly evaporate out into the universe. And after about a Google years, it's always bad when you use Google as a scientific number and not a search engine. But in about a Google years, even the largest, the supermassive black holes at the center of galaxies will evaporate, and there will be nothing in the universe except for a very dilute soup of elementary particles, neutrinos, the stray photon, things like that. So it's maybe I'm wrong. But yeah, that's based on that. That's projecting out what, if we understand what the universe is doing today correctly, which we might not. On that note, I had, in 1998, I got to have lunch with a very prominent cosmologist from Harvard. I won't name names. She looked me in the eye and said that cosmology was a dead field. Don't go into it. Because we understood it. We had these large-scale survey maps. We're going to figure out what dark matter is one of these days, but we basically have it. 1990, this was six months later, evidence for dark energy comes out, realizing that we know nothing about cosmology. So, Harvard. It's good school, not knocking it, but just, you know, you don't always get good advice.
One way in the back.
Yeah. That's okay. It's okay, I can hear you.
What did the ancients say or do about stars that went out or time?
Stars that went, I don't actually, that's a really darn good question. Oh, yeah, I'm sorry. What did the ancients do or know about stars that went out? It's interesting. The ones I do know about in 1056 AD, so this isn't exactly the ancients. This is after the people I was talking about, but before today. A star in the constellation of Taurus exploded. It died. It went away. Today, the remains of that star are the Crab Nebula. It was bright enough. The Chinese recorded it. In their records, it was bright enough to be seen during the day for 4 days, and they recorded it. My hunch is that, I'm not going to speculate because I could speculate, but I'd be completely guessing. So I'm going to admit my ignorance on that question. It's a darn good question. I think I'm going to look into it. With the exception of things going on, I know once you get into kind of more of the modern period, people noticed stars. I mean, that was how Tycho Brahe got a lot of his money. He talked about a new star that showed up. It was a nova that went off. A brand new star showed up, and he wrote a great book, and somehow, seeing a new star, he managed to convince the king to give him an island. I mean, that's salesmanship. I'm dancing around because I don't know the answer to your question. But I mean, there's got to be some record of something going on. I'm not sure offhand. I mean, the Crab Nebula supernova is the only one that really pops to my head. The Chinese recorded it. The Islamic world recorded it. Depending on who you listen to, the Navajo may have recorded it down in the American Southwest. European records don't really exist. It's not necessarily that they didn't see it. They may have been lost. It was also really cloudy. So, also, they weren't really, I mean, for the most part, you were kind of, you know, a yeoman dirt farmer at the time in Europe. So, really, prior to the scientific revolution, if you were going to place bets on which part of the world the scientific revolution was going to come from, you wouldn't be betting on Europe. So.
These are also exceedingly rare events.
Yeah.
Right.
Yeah.
Supernovae.
Yeah. I mean, honestly, if I wanted to just go out and I'll really be wrong, I bet that some of the comet records may have actually been like a supernova or something like that, a star blowing out. I wouldn't be surprised. So, excellent question, but no, don't know it. Yeah, I just rambled for, like, aren't humans amazing? I just rambled for like 3 minutes on something I knew nothing about. Awesome. I love my job. I love it.
Any other questions? Way back there.
Yeah, I can hear you. So when the stars are going out, so this is what, in connection with the how we're all going to die question earlier, right?
So I think that's the celestial sphere.
Oh, the celestial sphere. With Aristotle's model and so forth. It really was mechanized. I mean, it really was interconnecting circles where you'd have one sphere driving another sphere driving another sphere. Now, as Aristotle said, are these spheres real and invisible, or are we just kind of making them up? That's not clear, but it really was kind of a mechanized universe. The Greeks were really, really big on geometry. So if you could fit like circles and spheres inside of spheres inside of spheres. Now, Aristotle's model does have one drawback that has bothered a lot of people. That Aristotle's model, like I said, if you get the sphere of the stars spinning, it drives all of the others. If you want to think about it as little gears, you can think of it as little gears. You wouldn't be too far off. But here's a good question that you need to ask Aristotle. What's driving the sphere of stars? So Aristotle's model still needs what's considered a prime mover. Who knows? It's Greek. Maybe Zeus kicked it. You know, probably after he turned into a cow and a swan and a bunch of other things. So you still need someone to get the whole thing going. But provided you can get the sphere of the stars moving, those motions are transferred in from sphere to sphere to sphere. They're all on a common axis, but they spin at different rates. So you can think of them in that all these little extra spheres are the ones that are moving the spheres at different rates. Like I said, you can think of it as gears. It wouldn't necessarily be gears, but you know, there were some pretty amazing mechanistic works coming out of Greece around that time also. It's amazing what you do when you can just have people sit around and think. You get some really cool stuff, like little robots landing on comets. It's kind of cool. So,
actually, in that vein, I'm going to turn it to 2014. So, with that washing machine having landed on Comet 67P, can you tell a little bit about what maybe they may find, what may be the most exciting thing it may find?
all right.
Your opinion as a world expert relative to the solar system.
So actually, my project for over Thanksgiving break is to bring myself up to date on everything that we've learned from the Philae rover. A couple things we've already learned about it. One of the things is that the comet's very hard, like harder than you'd expect. So this is a comet that's going around the sun, and it's devolatilizing, which is a fancy way of saying, I want to close this out because I want to try to open something up here, which is kind of a fancy way of saying that it's been melting, it's been evaporating. So basically, the going idea is that the comet is freeze-dried. In a freeze-drying process, basically, the surface of the comet is going to be covered in a very fine powder, the same sort of regolith that we find on the moon. Lunar dust is a very, very fine material. It's about the same consistency of flour or talcum powder, except imagine like talcum powder made up of like ninja stars and broken glass. It's very abrasive. But we think that since this comet had been evaporating for so long, that below that dust should have been basically a frozen sponge, just made up of silicates and refractory material. The one signal I know we got back from the attempt to drill, even though that Philae was kind of like on its side like this, they still tried to drill the comet, and it was really hard. It was like hitting solid ice, so that's really surprising to me. That's something I would not have predicted. Going back, we really don't know anything about the surface of a comet, so this is all brand new stuff. The Deep Impact Probe, which we threw in a previous washing machine at full speed at a comet. Mike Alhern, I asked him, it's like, Mike, what's going to happen? He's like, I don't know. It's like, what's the lowest probability thing that you wouldn't be surprised? It's like, it could punch all the way through the comet. Okay? Mike Alhern is the leading comet guy in the country. And he's like, I've got this probe, I'm throwing something at a comet, I have no idea what's going to happen. That's why we threw it at. That's why we landed on the comet, because we don't know what's going to happen. Again, I just spent like 2 minutes talking about something I don't know. On that note, I do want to show one thing. This comet, the comet we landed on, 67P Churyumov-Gerasimenko, is a very special comet for me because I looked at it before it was cool. I can be like a comet hipster. My PhD work was done on pulling comets out of a sky survey that wasn't supposed to look at comets, but I figured out a way of pulling comets out of it. And one of the best comets that I found in the survey was 67P Churyumov-Gerasimenko, which I just thought was cool. And I was a little bit frustrated because it always broke all of my table formatting because it had just such a huge, huge name. And this talk is loading forever here. Let's see here. Dun, 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 dun. Picture's cool. I like it. There we go. Right here. Let's go to this. So this is a preview for my talk tomorrow. This is Comet 67P Churyumov-Gerasimenko as viewed in the Sloan Digital Sky Survey when I found it during my dissertation work. And this is a picture of its surface. I have no words. I'm utterly speechless. This is an object that I found, I published on, and now we have a robot on it. I have the coolest job in the world. Okay, no, Superman has the coolest job. I have the second coolest job in the world. So.
What is the percent of mass that would evaporate from this?
That's another thing we're trying to figure out. Fred Whipple put together the icy conglomerate model of the comet back in 1950s, and he gave the appropriate description that a comet is a dirty snowball. Under Whipple's idea that most of it would evaporate away. We've now sort of turned that on the head. We still use this idea, but now it's more of an icy dirt ball. That the comet probably only devolatilizes maybe about 20% of its mass, maybe only as little as 5%. The main thing is now we have to figure out if our freeze-dry model is even correct. The idea with this freeze-dry thing is that as you evaporate stuff away, it becomes very insulating. So after you devolatilize, after you evaporate off maybe 1 meter to 3 meters worth of icy material, this sort of rocky sponge that's left behind insulates the comet and chokes it off. And then the comet's going to go dead. Comets are a thing, your typical comet only has about 1,000 passes past the sun in it. Either it's going to devolatilize to the point where it's going to choke off and go away, and then we're going to think it's an asteroid, or it's going to encounter a planet and get chucked out of the solar system or into the sun, or it's going to devolatilize to the point where it falls apart. These things have almost no gravity. I mean, they have gravity, but it's so weak. That was Philae's issue, is that it had little harpoons that was going to fire into the comet to hold it there. The harpoons never fired. So Philae came down at only about 1 meter a second. What's 1 meter a second? So this is how fast Philae came towards the comet. It hit the comet and then bounced, came off at about this speed. This a bit of upward velocity took it 1 kilometer off of the comet and 1 kilometer down range. Yeah. You personally, no matter what shape you're in, every single one of you in this room, even me, could literally jump off this comet and never come back. Incredibly low gravity. So it doesn't take too much to disrupt them. If they all sort of melt away, they can come apart. We've seen a number of these. Shoemaker-Levy 9 came apart and plunged into Jupiter. Comet Schwarzmann-Bachmann 3 fell apart back in 2004, 2005. The solar observatories see comets all the time. They're falling apart as they come into the sun. So comets tend to die, and they tend to die very spectacularly sometimes. Otherwise, they just kind of go silent.
I think it was Whipple who suggested that biological molecules might be produced perhaps in comets and seeding the Earth as they pass by. Is there any, do people still believe in this idea? Is there any evidence? Yeah,
comets, meteorites, things like that. The carbonaceous chondrite, the Murchison meteorite. In 1969, not only did we land on the moon, but 2 very important rocks fell on the Earth. About 2 tons worth of little stones fell on just outside the Mexican village of Allende, and then a much smaller fall occurred out in the middle of nowhere in Australia. One of the reasons why meteorites have weird names is a lot of times they'll name them after the nearest post office. So Murchison was the nearest post office to where this meteorite found. Analysis of these meteorites are so primitive. They've never been heated. If you hold Allende or Murchison over a Bunsen burner, I'll slap you because you're destroying something. But they would actually sweat water. Murchison in particular, we found proteins and all sorts of all sorts of weird amino acids, all sorts of organic material. Nothing living, nothing creepy crawly, but the stuff we're made out of, we find it in meteorites. Moreover, now that we're getting better and better spectroscopy, we're also finding bizarro organic molecules just out in clouds of dust and gas. Some of these molecular clouds out in space, we find things like there's booze in space, alcohol in these clouds, formaldehyde, all sorts of buckyballs. We found buckyballs in space. That's awesome. These weird soccer-shaped carbon things. So yeah, the chemistry of life is out there all over the place. And this is one of the many reasons why astrobiology has gotten such traction. That just, the chemicals that make up the sacks of us aren't that uncommon. And even if you're incredibly pessimistic, and I'm pessimistic to the point where Frank Drake just rolls his eyes when I come into the room, my answer to the Drake equation is that we're the only intelligent life in like the nearest 10,000 galaxies. But even a horrible pessimist on life like myself has to say, you know what? Slime mold's probably pretty common. The stuff that makes up just single-celled stuff, it's all out there. And it happened early and often in our planet. Yeah, it took until the last 500 million years for life to get interesting here. But life has been here on this planet as long as we can find it. What's really surprising right now in my field, and just in the last 10, 15 years, the Mars rovers. I would be shocked if we found life today on the surface. The surface looks really, really dead. I'm almost to the point where I wouldn't be surprised if we someday uncover evidence of bacterial life on Mars. And I'm a huge extraterrestrial life pessimist. I think life is very uncommon. I think it's very hard for us to be here. But even a pessimist like me, I wouldn't be surprised. Under the ice of Europa, who knows? There could be fish. It's the Kraken. I don't know. We won't know till we go there. Again, we're to the point where like even the pessimists are going, gosh, I wouldn't be surprised if there's some sort of kind of single-cell life somewhere in the solar system. I mean, it's shocked that the words come out of my mouth, but yeah, so. Yeah.
Do you have a view on what made like humans say to be more intelligent than other animals or anything?
I don't know. I am not an evolutionary biologist, so I will duck that question. Keeping with the philosophy theme of this, there is a lively philosophical debate in metaphysics on the whole mind-body duality and the problem of consciousness. Is consciousness just a problem? You get enough chemicals together in your head and ba-doom, I think therefore I am, or is there something else? I'm going to sidestep that. I study rocks in space for a reason. So it's an excellent question, but I'm going to duck it.
And with that,